The EU has set a legally binding target to develop an economy with net zero greenhouse gas emissions by 2050. This target can be met through demand and supply side approaches to reducing the absolute energy consumption and CO2 emissions associated with the built environment. For glass, demand side approaches involve reducing absolute energy demand through improvements in building energy performance, behavioural changes to reduce energy-related activity, or using less material by design. These demand-side approaches can be directly influenced by designers and engineers. Supply-side approaches involve reducing the emission intensity per unit of energy associated with the manufacture of glass products, for example, through fuel switching to less carbon-intensive fuel sources. In this lecture, we will explain and discuss the effectiveness of these approaches in reducing the net environmental impact of the glass sector. Alternative raw materials. Architectural glass typically consists of 5 main constituent primary raw materials, which each play their own role to aid in glass manufacturability and ultimately impact the mechanical and aesthetic properties of the glass product. These include silica sand, sodium carbonate, calcium carbonate, feldspar, and dolomite. In the glass manufacturing process, the amount of CO2 released will depend on the emission intensity of the fuel source. In addition, CO2 is released as a byproduct upon thermal decomposition of the carbonate primary raw materials. Some manufacturers are investigating the use of pre-calcined materials, where the carbonate raw materials are preheated and the CO2 is captured more easily prior to glass production. New innovations are also emerging for new glass compositions that demand less heat or involve non-carbonate raw materials, such as zinc aluminosilicophosphates. Use of glass cullet. Increased recycling rates of post-consumer glass is one of the most readily available options to reducing emissions associated with glass production. However, at present, glass manufacturers typically use less than 5% of post-consumer glass cullet in new production. Emission savings are made throughout the manufacturing process when replacing 100% primary raw materials with 100% cullet. It is no longer necessary to extract and process primary raw materials, leading to 46% emission savings at the material sourcing stage. Cullet melts at a lower temperature than primary raw materials, so at the glass melting stage, less fuel is required to heat the raw materials, leading to reduced combustion emissions. In addition, the cullet has already undergone thermal decomposition, so there's a 100% saving in process emissions. Improved production yield. The float glass manufacturing line runs 24 hours a day, 365 days a year. The specification of different glass compositions and thicknesses, such as low iron glass or thin glass, can lead to the production of transition glass. Transition glass and offcuts associated with edge trimming are often collected as waste and recycled, albeit with additional processing required. Continuous improvements in quality control, or in some instances relaxing glass specifications for non-structural properties, would help to improve glass production yields. Float glass is produced in jumbo sheets and sold to downstream suppliers. The jumbo sheets will be trimmed into smaller dimensions for the desired product. Standardization and optimization of cutting processes will help to reduce the offcuts produced at the downstream stage and lead to higher fabrication yields and reduced emissions. Efficient structural design.
Another demand-side approach for reducing glass use is efficient structural design. As previously discussed, a large proportion of glass is typically produced in thin, flat sheets. These sheets have low resistance to out-of-plane bending, which means that when significant out-of-plane load occurs, designers tend to use thicker glass or laminate multiple sheets or plies. Alternatively, the stiffness and rigidity of a glass element can be increased by curving the glass. Another more experimental approach involves creating a composite system consisting of 2 glass sheets and a cavity, where a spacer bonded to the glass sheets, acts as a stiffening element. This design results in a lightweight structure with significantly greater bending rigidity than the combined rigidity of the individual layers. Such strategies improve stiffness and in-use performance, but come with certain implications. For example, curved glass requires additional energy for processing, increasing the energy required to manufacture it. Similarly, composite systems face challenges regarding end-of-life solutions. Therefore, careful consideration of the desired strategy is essential. Finally, designers must make informed decisions based on available manufacturing capabilities. Therefore, sound design is critical. For instance, it is often better to avoid longer glass elements with 5 layers of laminated glass, and instead introduce intermediate supports, limiting the laminated glass elements to 2 to 3 layers. The thickness of glass in most facades is very often governed not by the strength of the glass, but by the allowable deflection. Based on this limitation, a specific glass thickness is chosen to keep deflections within acceptable limits. These deflection limits are typically determined by what is considered acceptable to prevent occupants from feeling alarmed or worried. Current research indicates that occupants might feel comfortable with higher levels of deflection. This raises the question of whether deflection limits can be relaxed. If so, thinner glass could be used, reducing material consumption.
Improved building energy performance.
The type of glazing significantly impacts the energy performance of a building, especially its operational energy consumption. Using double or triple glazing and coatings can dramatically improve energy performance. However, this also increases the processing and embodied energy of the glazing unit. While this trade-off generally pays off, designers and engineers need to remain aware of the implications.
Occupant satisfaction.
Apart from energy efficiency, glazing units must also meet other critical occupant satisfaction criteria, such as acoustic, visual, and thermal comfort. When these needs are not met, occupants may attempt to manually adjust their environment to achieve a comfortable level, often increasing energy use in the process. If manual adjustments are insufficient and dissatisfaction persists, significant changes may be required, such as retrofitting or even replacing the facade. This highlights the complex interaction between occupants and the building envelope. This interplay is not always straightforward. For example, while occupants may prefer a clear, unobstructed view, managing solar gain might require shading. This raises important questions about balancing visual comfort and energy performance. Questions that are not easily answered and vary from one building to another.
Supply-side approaches. Architectural glass is commonly produced on a float glass line, which involves high temperatures and continuous operation year-round. This typically produces 600 tonnes of glass per day per production line. The provision of a reliable heat source is essential to avoid solidification of the glass melt, which will destroy the furnace. Float glass lines are typically powered by natural gas with electric boosting. The type of energy carrier and the direction the flames produce relative to the flow direction of the glass melt is essential. Alternative energy sources to natural gas are currently being explored, such as electric melting, oxy-fuel combustion, hydrogen, and liquid biofuels, as well as remediation options such as carbon capture and storage or utilisation. At present, none of the alternative gaseous energy carriers can be purchased at competitive prices compared to natural gas, owing to a limited supply.
Thank you for watching this open classroom video about Reduce, in which we explored the strategies to reduce the environmental impact of architectural glass. If you would like to learn more about the concept of sustainability in glass, have a look at the videos in this series our references, and further materials at the Open Glass platform.